Hello, everybody. In this video, we will go through a problem solution related to limit of a recursively defined sequence. And this is the for course MATH1251 at University of New South Wales. Now, in this question, this is question 66 and the part of the calculus part of that course. So we suppose the initial, we are going to start with the recursive definition. A1 is equal to 1, and an plus 1 is defined as a square root of an plus 1. So n's are denoting here are the natural numbers, and in this equation, n is bigger than equal to 1. If we have indices of a sequence defined on natural numbers, whatever the proof that we are going to do is most likely, almost definitely, to use an induction method. This is what is it for. So all the method that we are going to use will be the induction for this question as well. It is obvious when we are reading the question, observing that the indices are the natural numbers without looking at anything else. Okay, what we need to prove here, we would like to prove that this sequence is bounded and increasing. Since it is a sequence bounded and monotone increasing, then there exists a limit. That's the first thing that we would like to show. Another thing is we would like to show that to find out the actual limit. Let's start. Now, first, let's try to find that this definition gives us an increasing function, which means that we would like to show an is smaller than an plus 1 for all n. Again, as I said, the method will be an induction method. The first step, we need to prove that n is the smallest possible n when you start will be satisfying that condition. So for us, a1 is equal to 1, which is given to us. So the equation that we can use is for n is equal to 2. So a2 is equal to square root of 1 plus 1, which is square root of 1, which is really bigger than 1, which is a1. So it is satisfied. So for the smallest step, it is satisfied. As an induction hypothesis, we assume that this is true for some k, with ak is smaller than ak plus 1. Now we would like to prove that for the case ak plus 1, we would like to use induction hypothesis to prove this one. So from induction hypothesis, we have ak plus 1. I'm going to add 1 on both sides and taking a square root. This is what I'm doing here. Adding 1 on both sides, which is perfectly fine because 1 is a positive, and also taking the square root. I am allowed to do that too. And this part will be ak plus 1, and this part will be ak plus 2. So the ak plus 1 step of this inequality will be ak plus 1 smaller than ak plus 2, which is what we wanted to prove. So all of these shows that the sequence is increasing sequence. Right, that is done. Now we would like to prove that it is bounded. Now you need to find out the bound by yourself in this case. Anything, I could have choose 3 or anything like that too, but the 2 works. I would like to prove my claim now. So it is bounded by 2. And I would like to use induction method to prove this claim. The claim is an is smaller than 2 for all n. For k is equal to 2, this is a2 square root of 1 plus 1. This is square root of 2, always smaller than 2. The first step in the induction hypothesis is being satisfied. Now, induction hypothesis, which means that for some k, ak is smaller than 2, is satisfied. Now, we would like to prove as an induction method for k plus 1. ak plus 1, by definition, is a square root of ak plus 1. If we take the squares on both sides, I have AK plus 1 square from here, and I have AK plus 1 over that side. Since AK is smaller than 2, I'm using this induction hypothesis in this step, and I have 1 here. So I have AK plus 1 AK plus 1 is smaller than 3. Now, with this, I'm taking the square root. So I have AK plus 1 on the left-hand side. I have square root of 3, which is smaller than 2. So this is true for all n. So an is smaller than 2. An, the sequence is defined in that way, is increasing and bounded. It means that there exists a limit. There exists a theorem, which we know it from our lectures. An is a monotone increasing and bounded above, then there exists a limit. Now, if we have a limit, then we can call a number because that number exists. Let's call it L. Now, the idea is that infinite plus 1, infinite minus 1 will not change to infinity. So you can add an infinity 1 or a number, it will be still an infinite. Or if you subtract an infinite from a number, that will be still infinite because it's an infinite, but it will not change. So in the infinite situation, this n goes to the infinity, is an is equal to n goes to the infinity, an plus 1 will also be satisfy the same condition. It means with this thought, we will have L is equal to square root of L plus 1, which was the definition. And this is the condition in the infinity, at infinity. When n goes to the infinity, this is the equation that we have. We are in the limit condition. Now, taking a square, we have an equation. We have a polynomial equation, and we can solve this polynomial equation. And we will find the roots of this polynomial, which is 1 minus plus root 5 over 2. Now, let's have a look what does it mean for us, right? So if we think about the root 1 minus square root of 5 over 2, this is a number which is minus 0.618, which is smaller than 1. But L1 cannot be limited, cannot be the limit of an, because an is bounded below by 1. This was the definition of it, right? This is from the beginning. That's how it's defined. The A1 is equal to 1. You're starting with the 1, and the limit cannot be out of the range of that sequence. So the L1 cannot be taken as a limit. It is impossible. It cannot be. So L2, the number 1 plus square root of 5 divided by 2, which is 1.618, is the limit. That's what it is. And it is consistent what we found. What we found is that this limit needs to be between 1 and 2. The part A shows that every sequence element is smaller than 2. So the limit needs to be smaller than 2. So this is a hint for us what the limit should be. And the limit here, 1.618 between 1 and 2, what are the boundaries of this sequence? That is the limit for that sequence. Thank you very much. That's all for this question. I hope it is useful for everyone. Thank you very much for listening.